In this video, we're going to talk about the process of sampling, which is basically collecting data or information to try to answer some question that we might have that we want to answer. Before we jump into sampling, though, I want to talk about some of the big picture ideas of statistics in general. I know a lot of people are probably apprehensive about taking a math class, and especially in this case, taking a math class online. It's a lot more difficult to do, and you can't raise your hand and ask questions as we move along. So I think having a sense of kind of the big picture of what's going on hopefully will help guide you as we start to move through this class. And so I want to focus, before we jump into the actual book material, I want to focus on two particular words. I want to talk about statistics versus probability. So before we jump into the book stuff, let's look at statistics versus probability. Probability. When I first took a statistics class, as far as I was aware, these two words were completely synonymous. They meant the same thing. I didn't understand that there was a distinction. But in fact, there is a distinction. They're different, but you can think of them as sort of two sides of the same coin. So let's start with the idea of statistics, since that's the name of this class. So statistics is backwards looking. And what I mean by backwards looking is statistics is the process of looking at data and outcomes that have already occurred. So basically, when we have our set of data and we're trying to compute what we are calling statistics on it, that data has already, it comes from something that's happened in the past, a poll that occurred, or an experiment that happened in the past. So the data that we're interested in statistics is typically comes from an event that's already occurred. So something that's already happened. Probability, on the other hand, is forward-looking. Probability is all about trying to predict what is going to happen in the future. So it is forward-looking. And in this case, we want to predict what is likely to happen. Let me say that, not what might happen, but what is likely to happen in the future. And it's when we put these two ideas together that they become really, really powerful. And that's going to be sort of the arc of this entire class. We're going to start with statistics, stuff that is backwards looking. We're going to talk about data. We're going to talk about how to collect that data, which is the exact topic that we're going to cover here. That's what sampling is. So how do we collect data? What does that data look like? Where does it come from? And what types of things can we do? How can we describe that data? And we'll use that to kind of come up with a picture of how we think things work, a model based on the information that we've collected of how we think, whatever we're studying, how we think things work. And we'll use that model of how we think things work to try to guess or predict what might happen in the future. So we're going to conjoin statistics and probability together as a really powerful tool to try to make predictions. So together, they're really powerful. And in fact, they mirror the way that humans learn. They mirror the process of human learning. So this idea isn't just about math. It's pretty much as much about psychology and neuroscience. The way that humans learn, by and large, is by encountering things, having experiences, and using all of these experiences, everything that's happened in your past, those shape your model of the way that the world works. All of your experiences, all of your encounters, all of your conversations with other people, they inform how things work. You know how to read somebody's face when they make a certain face, and you recognize their muscles in their face a certain way, and it's a certain type of frown. You know that that means that they're sad, and you know that that means maybe they'll be helped out if you comfort them. Humans are really good at learning from past experiences to try to make predictions about what's going on now or what's going to happen in the future. So this is the way we learn. We internalize experiences, data, information that comes from our past. We use that to make a model of how we think things work. And then we use our model of how we think the world works to make decisions moving forward. When you encounter a new situation, you're interacting with a new person, you take your previous interactions as a model to dictate how you should interact with this new person. And this process is identical to the process that we're going to be talking about and formalizing and quantifying and applying math to, that is the process of using statistics and probability. So in human learning, we take an info, / experiences. We use them to form a model of how the world works. And then we use that to make decisions. In novel situations. Sorry for running off the board there. Let's sneak that over. Novel situations. So this is the process of human learning, and it mirrors the process of statistics. So with that in mind, let me jump into the idea of sampling. So let's go get back into sampling. Let me scroll up here. So none of this was really in the book. These are just kind of big picture ideas that'll help if you keep them in mind as we move through this course. The entire course is building on one component or another of this process of collecting information, of forming a model, or of using that model to make predictions. That's what we're going to be doing this entire semester. Okay, so jumping into the book, I wanted to actually start with the book's definition of statistics. It's a little bit different than the one that I wrote up there, but it's pretty much captures a lot of the same ideas. So the book's definition of statistics is that statistics is the study, so statistics as a science, is the study of the procedures for collecting, describing, and ultimately drawing conclusions from information. So you can see their definition's different, but it involves a lot of the same things. So we're going to talk about how to collect data, how we can describe or summarize that data, and then how we can use that data to draw conclusions. And this leads us up to the point, once we've drawn those conclusions, we've kind of built our model for how we think things work, and we can start to implement the concepts of probability to make predictions based on all of this. So, For now, as we talk about sampling, when we talk about sampling, we're focusing all of our energy on this part, on the collection of data. So sampling is about collecting data. Okay, so to do this, to have a fruitful discussion, there's some jargon, some words that are sciencey words that I want to give formal definitions to in addition to statistics. So I know this is going to be cumbersome. I'm just writing a lot, so bear with me. The first thing I want to talk about is a population. The population is whatever we're trying to study. Oftentimes it will be a group of people. When we talk about population in everyday English, usually we're referring to like the population of the state of New Mexico, or the population of the United States, or the population of the whole world. It doesn't have to refer to people though. So when I say that population is the entire collection of individuals that we're interested in studying, so it's the entire collection of individuals that we want to study. You'll see this down the line. When I use the word individuals, again, it doesn't have to refer to people. If we're a biologist, maybe the population that we're interested in is a population of bacteria, and the individuals that we're talking about refer to individual bacteria. Maybe we're a geologist and we're studying rocks, and the population is the entire collection of rocks that we're in some geologic formation that we're interested in studying. So the word individuals, we kind of have to loosen our definition a little bit. It doesn't necessarily refer to people. It often will, but it's broader than that. Another word that's going to be hopefully self-evidently important is the word sample. So I need to define what a sample is if we're going to talk about sampling. The sample is the subset of the population, and I'll come back to that word subset in a minute. The subset of the population that actually gets observed. As part of our study. So subset just means that it's a group of individuals, not the whole group, but it's all individuals that come from the population. So the population is a large group of individuals. The sample is a smaller group of individuals that are picked out of that big group. That's all the word subset means. Subset of the population means the individuals I'm picking are all coming from the population. Hypothetically, let's think about a situation that is relevant right now. The U.S. presidential and other election campaign that's going on right now. So Donald Trump, Joe Biden, they're running for president. There's a ton of other races for all the House of Representatives and various senators and local positions. If we want to try to study the U.S. voting population, the people that plan to vote in the upcoming election, it's not going to be possible to study everybody. There are probably going to be in the ballpark of 150 million people that wind up voting in the upcoming election. And if we want to do a study to try to predict the results of that election before it happens, there is no way that we're going to be able to actually go out and talk to all 150 million of those people that wind up voting. It's not feasible. It's going to be too expensive, too time-consuming. We'll never get it done. By the time we finish, the election will probably already have occurred and be over. In fact, that's what the election is for. The election is basically a big sample, a big survey of people in the US, asking them who they want to lead the country. And we might as well just, if we were going to take a poll and ask everybody, every single person that's going to vote, who they're going to vote for, we might as well just have that be the election. Why do it all over again a couple months later? So this is the idea. If we want to try to make predictions about what's going to happen in the overall election, it's impossible to talk to the entire population. The population of US voters is 150 million people. Instead, we will take a sample, a smaller group of individuals that are a subset of those 150 million, but maybe it's only 1,000 people, or maybe it's 5,000 people. And we'll use the results of our sample to try to make predictions about the population. So this is the idea. In general, the reason that we want to sample, we sample not because we're interested in specifically the outcomes of that sample, but because we want to use that sample as a gauge for what the entire population is going to do. So we sample because the entire population is too hard to study. Directly. Right? We can't talk to all 150 million people for whatever reasons. It's too hard, too expensive, too time-consuming, whatever. So this is always the point. When we take a sample, we want our sample to be reflective of the population. What I mean by that is I want the sample to look as much like the population as possible. Obviously, it's going to be smaller, but I want a similar number of Republicans and Democrats and independents, a similar number of men, when I say number, I should say proportion, a similar proportion of each political party in my sample as are in the actual population. I want a similar proportion of men versus women in the sample as in the overall population. I want a similar proportion of people that live in cities versus country in the sample that matches that of the population. We want our sample to look as much like the population, just scaled down, as possible. So that is our goal. So how do we get a sample that looks like the population? Well, this is a really interesting question, and it's one that I'm going to let you guys discuss a little bit in the discussion section for this module. But suffice it to say, it can be hard. So let me give you one example of why this might be difficult. Let's say we want to study the exact question I've been talking about. I want to try to make a prediction for the outcome of this upcoming election, again, before it occurs. How do we conduct this sample? How do we find people that can answer our poll and without somehow skewing the results? So think about trying to do it face-to-face. You want to randomly pick people face-to-face. Well, that's going to be really difficult because, again, we want our population to be reflective of, or our sample to be reflective of the population. The population's spread out all over the country. There's no way that if we're doing a face-to-face survey that we're just going to travel town to town over the whole country. That's going to be, again, very expensive and time-consuming. So probably face-to-face isn't really going to work. If instead we decided, let's just not travel, let's just survey people here in Albuquerque. Well, there's issues with that. Surveying people in Albuquerque, you're going to get a skewed population. It's not going to be reflective of the country as a whole. So I'm going to let you guys discuss that again a little bit in the discussion section. And hopefully you can kind of figure that out. But our ultimate goal is to come up with what we call a simple random sample. A simple random sample is one that basically, if we totally select people totally randomly, we should get something that just due to chance matches the overall US population that we're trying to study. So by doing it randomly, randomness ensures that we're not intentionally or unintentionally skewing our data in some way. So keep this in mind. I'm going to define a simple random sample. It's going to be a mathematical definition, but I'll try to explain it after I'm done writing. So a simple random sample of size n, and n is just going to be a placeholder for a number. Maybe we want to sample 1,000 people, so in that case, n would be 1,000. So a simple random sample of size n is one that's chosen via a method. There's different ways to do it, but a method in which every combination every combo of n individuals from the population is equally likely to be drawn. And just fair warning, I'm not going to make you recite definitions on any exams or anything like that. I just want you to have a sense of what these things are and be able to kind of identify one when you see one. That's kind of the idea. So don't worry about memorizing these definitions verbatim. I'm kind of making up this definition as I go a little bit, so don't worry about the wording. But it's a very mathematical definition, the way that they've described this. This is close to what the book says. What they're saying is, in this case, if we let n be 1,000, our simple random sample of 1,000 people is one that's chosen using a method where every other possible combination of 1,000 people in the US was just as likely to occur as the 1,000 people that we actually happened to pick. This is a mathematical definition of the word random, basically. What does it mean for something to be random? We all have a sense of what that means, but it's actually a really hard thing to define. And so this is an attempt at defining what it means for something to be random. We didn't pick our group of 1,000 people that was somehow more likely to be picked than a different group. That would be skewing the results. So, we didn't pick the 1,000 people just off of C&M's campus because that was convenient. That would be skewing the result, and we would have been more likely to have picked that group of individuals than a group of individuals spread out across the entire country, so to speak. So this is the idea. If the group that winds up getting picked was just as likely as any other group to get picked, that defines it as a simple random sample. So things like this turns out really, really difficult to do in practice. And again, that's gonna speak to the discussion post that I want you guys to get into. But I can say that in certain contexts, it's not that hard to pull off. So if we wanted a simple random sample and the population that we were studying was just the students in this class. So as an example, if I just wanted, so if the population is just, and I'm going to abbreviate population, POP, is just the students in our class. So if that's what I want to study the students in our class, and I want to take a sample. We can sample by drawing names out of a hat. That would be totally random, right? I write everybody's name on a equally sized slip of paper, put them in a hat, mix them up, and start pulling out names. That's as random as we can get. So if you think about it, we're pulling names out of a hat. Why can't we do that for the population of all citizens in the entire United States? Well, you're going to have a lot of trouble tracking down those individuals, even if you could pull out their names. And how do we even get a list of the names of everybody in the U.S.? We have maybe a list of numbers, social security numbers, but people don't necessarily want those given out anyways. So this isn't really feasible to do in really large scales. It's something that can be done here if we're only talking 30 people, 100 people. That's feasible if that's the size of our population that we're sampling from. But if there's 30 people in a class and we randomly pull out 5 names, we have successfully randomly sampled that class. So that is the idea here. So again, executing a simple random sample can be difficult. Hopefully, as you go through the discussion post and try to think about it, you're going to see how difficult it can be. But as an alternative, we're going to need to come up with another approach. And that other approach is what's called a sample. So samples of convenience. And samples of convenience are ones that are drawn that aren't a simple random sample. So basically anything that's not a simple random sample is some sort of sample of convenience. A sample of convenience is one not drawn using a well-defined random method, which again is not a super helpful definition. Well-defined random method. But the gist of it is that a sample of convenience is one where we're sacrificing randomness for the sake of convenience. So essentially, this is the distinguishing feature. We sacrifice randomness for the sake of convenience, hence the name. So an example that I like to give for this is, imagine that we are health inspectors at a grocery store, and it's our job to go inspect all the gallons of milk that are back in the big walk-in refrigerator, and make sure that the milk isn't, expired or something like that. So we want to check the big stack of milk at a grocery store for the expiration dates. And imagine that you get back there and they're stacked in these crates, piled maybe, 5 feet high. And you're looking at this giant stack. So it's 5 feet high, maybe it's 10 feet wide, 10 feet deep. Which milks are you going to actually look at? Are you going to take down all these crates of milk to try to get to the bottom middle milk gallon and check its expiration date? Probably not. And so instead of trying to look totally randomly throughout this pile of milk, maybe we'll just kind of go around the perimeter and look as randomly as possible at the ones that are convenient to see, the ones that we can read the dates without having to move everything. So we're checking our stack of milk at the grocery store for expiration dates. We only check the easily accessible ones. That we don't need to move anything to get to. And this is fine. We can do samples of convenience as long as there's no reason to suspect that there's some systematic difference between the gallons of milk in this case that we are checking and the ones that we're skipping. So, for example, if all these gallons of milk, if we know they all came in one shipment off of one truck from one farm, or one processing plant, then that's probably fine. But if it's stacked in such a way that there was one delivery and then the second delivery got stacked sort of around or on top of that one, and we're not checking any of the first delivery, we're only checking the second delivery, then this is probably a bad idea. So as long as there's no reason to suspect that there's some systematic difference from what is getting checked versus what's getting skipped, this is probably fine. But if there is a reason to suspect that there could be a difference, like in this case the milk came from 2 different shipments, then maybe this isn't a good approach. So just keep that in mind. As sort of subcategories of this, or as other approaches, there's other methods of sampling. And these other methods aren't, so they're not simple random samples, and they're all sort of subcategories of samples of convenience. And they all serve a different purpose. So the next one I want to talk about is something called a stratified sample. And in a stratified sample, the population is, so it is one in which, the main population is going to be broken into groups where there's some commonality within each group, but differences between the different groups. Which the population is broken into groups based on some sort of distinctions that make the groups different from one another. And what I mean is, obviously they're different individuals, but that there's different characteristics of the different groups. Then each of those individual groups is randomly sampled. Okay. So why would we want to do this? One good example is maybe we're interested in studying something related to employee satisfaction at a company like Amazon. So, employee satisfaction survey at a big company like Amazon. Amazon has a lot of different employees and a lot of different types of employees. There are warehouse workers, there are delivery people, there are engineers that maintain the website, there are engineers that work on the Amazon Prime Video and music, so there's technicians, there's managers, there's executives, the CEO, all the way up to Jeff Bezos. All of these different groups, probably it doesn't make sense to talk to them as one big group and see how satisfied they are with their work environment. Probably Jeff Bezos's impression and the other executives' impression of, how nice their office is going to be very different from those warehouse workers. And so it makes sense to break the group up into a bunch of different groups where each of those groups has some sort of commonality within the group. So we break them into maybe the executives, the engineers, whatever managers, warehouse workers, etc. Then sample each of those groups. And we'll get a better picture. And that way we can weight sort of in proportion. There's probably 1,000 times or more, 10,000 times as many warehouse workers as there are executives. So if we're trying to do a whole company survey, I probably need to make sure that I don't sample 10 executives and 10 warehouse workers. I should sample, 3 executives and 3,000 or 30,000 warehouse workers or something like that. We should do it in proportion. So this is the idea. We break up a big group into a bunch of strata. That's why it's called stratified. The groups, each group has some sort of commonality within that group that makes them distinct from the other groups. And that gives us a reason of why we might want to get their opinions or study them separately. The next type of survey or sample that we can take is called a cluster sample. And a cluster sample is also one where we break the population into groups. So a cluster sample is one in which the population is split into groups in some way. Then we randomly pick which groups we're going to observe. Or collect data from. And we sample every individual within those selected groups. Okay, so on its surface, it's kind of hard to distinguish from a stratified sample, but it's very different in the way that it's conducted. So in this case, in a stratified sample, we broke the population into a bunch of groups. We look at all of the groups, and we randomly sample within all of the groups. So we don't look at every member of every group, but we do look at some members of every group in a stratified sample. In a cluster sample, we're going to break the population into groups. And we're going to pick which groups we're going to look at. We're not going to look at all the groups. So we're going to randomly pick just some of the groups to observe. But once we pick those groups, we're going to talk to every individual within that group. So a good example of this, these happen in a lot of like government surveys, stuff related to kind of the census, things of that nature. But imagine that we wanted to do some sort of a door-to-door survey. We might break the city of Albuquerque. So we want to do a survey on a proposed property tax increase in Albuquerque. Door-to-door survey on property tax hike in Albuquerque. What we might do is randomly pick just a handful of neighborhoods. So I don't want to totally randomly do a total random sample and do a door-to-door survey, because that would have me driving all over the city, back and forth. I'd knock on somebody's door in the South Valley, then I'd have to drive to Nob Hill, then I'd have to drive out to Taylor Ranch, then I'd have to drive up to the Heights, then I'd have to come back to the International District, then I'd have to go to Nob Hill, and we'd be driving all over the place. So instead, let's just randomly pick like 5 neighborhoods, and then let's walk through those and go literally door to door and knock on every door in that neighborhood to do our survey. So let's randomly pick, instead of, 5 out of, I don't know how many neighborhoods there actually are in Albuquerque, but let's say hypothetically 5 out of 50 neighborhoods. Then knock on every door in those selected neighborhoods. And this would be much more efficient because it doesn't involve driving across the city. Once I knock on one door, my next sample is the next door neighbor. I can literally walk, 50 feet and be at the next door. So this is the idea of a cluster sample. So just to distinguish them from a stratified sample one more time, in structure, the way they structurally differ, in both cases, we're breaking the population into groups. In a stratified sample, I'm going to look at every group, but not every member of every group. So I'm going to look at all the groups, and I'm going to randomly sample within those groups. In a cluster sample, I'm going to do the random sample at a level above that. I'm going to randomly sample which groups to even look at. I'm not going to look at all the groups. And then I'm just going to then I'm going to talk to every individual within the groups that do wind up getting selected. So that's the distinction between a stratified sample and a cluster sample. And again, all of these things, as you can kind of see, they're for convenience in some manner. The last couple that I want to do, I think we've got 2 left here. We can be done with this video. So the next one is systematic sampling. And this one's pretty easy to remember. A systematic sample is one where every, say, nth or kth, whatever letter we want to use, I'll use n again. Every nth item on some list, and I'm going to put the word list in quotation marks, because it doesn't have to be literally like a list on a sheet of paper. On some list is sampled. Where that list is created in some convenient way. Okay. So what do I mean by this? So you can have a list, a physical sheet of paper with names on it, and just pick every 5th person on that list, or every 10th person on that list, or every 17th. Pick whatever value you want for n. Again, n is just a placeholder for some number that happens to be convenient. But where this often occurs is in situations where the list is generated naturally, like the order that things come off of an assembly line. So the list, in quotes, is just the order that maybe iPhones come off an assembly line. And maybe it's our job to check them to make sure, for quality control purposes, that they turn on, that the screen, there's no dead pixels, whatever the case may be. So we check maybe every, 18th phone off that assembly line for quality control purposes. So just for quality control. Okay, and this is nice because it means that maybe the assembly line pops out 18 phones a minute. So we have exactly a minute to check, and by design, that's exactly how long it takes for us to check all the features that we need to check on the phone. And so by the time we finish checking our phone and put it back on the line, the next one that we're supposed to check is coming along right then. There's no downtime, no waiting. We don't have to do it at random intervals where maybe sometimes we have to stop the assembly line to check 2 in a row because that's what we were supposed to do because it randomly told us to do 2 in a row. And sometimes we have to wait 5 minutes between phones because it's saying don't check for another 100 phones. By doing it at this even increment in time, or even increment in value off the list, it can ensure that there is no downtime and that it can be done as efficiently as possible. So all of these are different approaches for sampling. The last one I want to talk about is what's called a voluntary response sample. all the other methods that we've talked about so far have a purpose and can be used potentially in some sort of scientific setting. A voluntary response sample is pretty much just for fun. So it's exactly what it sounds like. A voluntary response sample is one in which people volunteer their opinion. So examples of this are things like, like a Twitter poll, or something like, the voting systems on American Idol. The scary thing is, in a sense, a voluntary response sample is exactly the format of the actual U.S. election. People go to the polls to volunteer their opinion about who should get picked. So we've got Twitter polls, American Idol, things like Yelp reviews. Right? And the idea is, the reason these are unreliable a lot of people do go to the polls. So I guess there's, that if anything, there's a bonus to the polarization in our country right now, is it motivates a lot of people to go to the polls.